So this is the beginning of chapter 2 and synapses, and I'm going to start, as your author does, by talking about the concept of a synapse, so really how we discovered the properties of synapses. It was Charles Scott Sherrington in 1906 who inferred the major properties of synapses, and he did this, so he made these inferences from the behavior of dogs. This is pretty impressive. He got this pretty spot on. And this happened about a half a century before any technology existed that would have allowed us to measure the properties of synapses. So he was looking at the reflexes of dogs, and what he would do is he would have them kind of strapped up, and he could get underneath them and pinch their foot or their paw. And the dog, that pinched paw, the dog would flex that leg or pull it back toward him or herself and extend the other three legs. And from this behavior, Sherrington proposed a reflex arc, and this is how we know the reflexes work here in the spinal cord. So this circuit that starts with the sensory neuron, feeling that pinch, to another neuron, so we're going to call that an interneuron, one that's within the nervous system, and then that interneuron is going to communicate to a motor neuron, causing the reflex of flexing away. So what that reflex arc shows, Sherrington is proposing that it is the spinal cord controlling the flexion and extension reflexes. He also made several important observations about these reflexes. So that they are slower than conduction along the axon. So what we've talked about so far with neural communication in chapter 1 was that conduction of the electrical impulse down the axon, and that happens really quite quickly. And what's happening at the synapses, that communication is slower. Second, that he could use several weaker stimuli and present them at different times and different locations, and then he would see a stronger reflex than if he just used a single stimulus. And finally, when one set of muscles becomes excited, another set of muscles becomes relaxed. So I'm going to walk you through each of those observations with a little bit more detail. The speed of conduction through the reflex arc was never more than about 15 meters per second, whereas action potential velocities are at about 40 meters per second. So he assumed that this delay must be where one neuron is communicating with another neuron. And what's being shown in the picture to the right is the speed of conduction along an axon at about 40 meters per second. So we're looking at A communicating to getting to B, but then we're looking at this reflex arc, C to D to E, so the sensory nerve to the interneuron to the motor neuron, and that reflex arc was slower and more variable. Again, suggesting this place where neurons have to communicate. If you remember, the second observation was that several weak stimuli, whether they are at different places, different locations, or at different times, they produced a stronger response than a single stimulus. And so he actually looked at temporal summation and spatial summation, where temporal summation is across time. And I'm going to continue throughout the class using temporal as that vocabulary for through time. So while a light pinch did not produce the reflex, a few rapidly repeated pinches did. And so that single pinch transmission to the postsynaptic neuron, he assumed this was subthreshold excitation. Okay, this is where we get this idea of these potentials being graded, that we're getting graded depolarizations, and we need to reach that threshold of excitation. And what we're looking at here are those excitatory postsynaptic potentials, or what I'm going to continue to abbreviate here as EPSPs. And what's being shown over to the right is, so this was all really inferred by Sherrington, but in 1964, John Eccles performed the measurements, and we can see that with one pinch, you can see in the change in voltage, we see a small change in voltage. Then we get the second very rapidly after that first one. We see more change. And if we get 3 pinches, 3 in a row really quickly, that we reach at that point the threshold of excitation, and that's where we see the action potential. And again, this can happen across time, where we get 3 pinches or 3 stimuli quickly, right in a row, so that kind of temporal summation. Or this can occur across space, where we get 3 different pinches in 3 different locations that are close enough together that they're influencing the same neurons. So this kind of spatial summation. And the picture's just showing the same kind of thing. If I just have 1 pinch, I'm sub-threshold. 2 pinches, I'm still sub-threshold. And the 3 pinches got us to the threshold of excitation, and the neuron sent its action potential. Temporal and spatial summation can occur together, and they often do. And how they get summed together can depend on the order of the stimuli. So the strength of the summation can depend on the direction or the order of the stimuli. So what the pictures are showing here is, if you see the first, second, third, fourth on the left-hand axon that you're looking at. So if the one that says first, it gets its stimulation first, and then the second, and then the third, and then the fourth, in that order, those are going to continue to sum together to get a pretty large depolarization, because they're really kind of coming in, if you will, along at the same time, because the first one is starting farther away and then meeting up with the second and the third and the fourth. Whereas if we look at the neuron on the right, where the first is closer to the soma, to the cell body, and then the second is farther, and the third is farther, and the fourth is farther, that first one can come along, we get the graded depolarization, and then we start to lose some of that. The second comes along, we get a graded depolarization, but we start to lose some of that. So that one's going to be a weaker depolarization. And again, this is summing together. So with 4 stimuli, we still might see that we get to the threshold of excitation and send an action potential. But if we say, let's say there were 3 instead, potentially maybe not. So it depends on whether or not we get to that threshold of excitation, but how those are summing together can influence the likelihood. If you remember the third observation, Sherrington's third observation was that as one set of muscles was excited, another set of muscles was relaxed. Okay, so he inferred this from a pinch on one foot, sending a message along to a sensory neuron to an interneuron in the spinal cord. We see then excitatory activity between the interneuron to the motor neurons connected to the flexor muscles. So when I'm pinching that paw, I'm going to send excitatory information to the flexor muscles, as that dog is going to pull their paw away in this flexion response. And it's going to send excitatory activity to the extensor muscles of the other 3 legs. So we saw those other 3 legs extend. That interneuron is also inhibiting the activity of the motor neurons to the extensor muscles of the leg that flexed. As that leg's flexing, the extensor muscles are relaxing, and those other 3 legs that are extending, their flexor muscles are relaxing. So that interneuron is also sending inhibitory activation to the flexor muscles of those other 3 legs. And here we're talking about those hyperpolarizations or graded hyperpolarizations, also called inhibitory postsynaptic potentials, which I'll start to usually shorten on these slides to IPSPs. And again, the picture to the right is just showing some excitatory postsynaptic potential, that kind of summation to where we get to the threshold of excitation and send our action potential. And then at the very end there, I think it's number 5, it's showing an inhibitory postsynaptic potential. And so far we have been keeping things really simple and looking at single neurons and showing this kind of summation. But remember what I said before about reaching the threshold of excitation, that we are summing, usually from hundreds, maybe thousands of neurons. We are summing these excitatory postsynaptic potentials, so this excitatory information, and inhibitory postsynaptic potentials. So this inhibitory information in this kind of neural integration. And if after I integrate, and this can come in, again, we can have a temporal summation, we can have a spatial summation, the timing is important, the direction is important. If I reach my threshold of excitation, then I fire. And again, this is the idea of neural integration. And what the picture is showing is the neuron that's kind of at the top left. It is communicating, the green is meant to be excitatory information. It's communicating excitatory information to the neuron that's on the farther right. And we're going to see if that neuron fires, but it's also sending excitatory information to this small little interneuron that we see in between. And that interneuron, if you can see that it's got a red there at the synapse, that is showing that that neuron is sending inhibitory information. So maybe we're less likely to fire the final postsynaptic neuron because it's receiving excitatory and inhibitory information, but it's going to be getting this from many, many neurons. And Callett took this out of the book. This was in a previous edition, but I found it really helpful for talking about neural integration. And I feel like that neural integration is something that students don't seem to completely understand, and they tend to not ever talk about again, or they tend to forget. So I'm going to go through these diagrams because it's a good reminder, again, about how these excitatory postsynaptic potentials and these inhibitory postsynaptic potentials can potentially work together to influence the postsynaptic neuron. So in this case, the postsynaptic neuron we're looking at is X, and we're asking, is X going to fire? And if you look up at the top right in figure 3.9, this is one where the threshold for X is 1, and he calls this an A or B. Either A or B is going to give me a response. So A sends 1 unit of activation, B sends 1 unit of activation, and if either A or B are sending activation to X, X is going to respond. If A and B are sending activation to X, if you remember from our when do I actually fire and how do I communicate signal strength, if they're both sending information to X, X is going to fire more quickly. We go down to figure 3.10. This is an A and B response. So now the threshold for the neuron X is 2. If A sends its 1 unit of activation to X, X does not fire. If B sends its 1 unit of activation to X, X does not fire. It's only when A and B both are sending activation to X that X fires. And then figure 3.11, if you move over to the left at the bottom there, this is a diagram for A and B, if not C. So we still have the threshold for X is 2. If A sends its 1 unit, X does not fire. If B sends its 1 unit, X does not fire. If A and B each send their 1 unit so that it gets 2 units, X fires. But you can see that C has this inhibitory activation towards X. And so if A, B, and C, we get +1, +1, we get to 2, -1, we go back down to 1. Now X is not going to fire again. And again, these can get really, really complicated, but these are nice, simple diagrams to show the basic idea of how this is working.